Hello everyone, my name is Tara Josberger and I will be discussing coral bleaching mitigation strategies. Alright, just to get started, a little summary information. Coral reefs are some of the most productive and important ecosystems on the planet. As temperatures rise in our oceans due to increased concentrations of atmospheric greenhouse gases, the frequency and intensity of coral bleaching has also increased. Coral bleaching is the expulsion of symbiotic algae that live within the coral and provide their color as well as their food. Several strategies to mitigate bleaching have been important topics of research. Here I will divulge into 4 mitigation strategies. First, the use of marine protected areas, and then we will discuss shading. Third is the use of exogenous antioxidants to combat reactive oxygen series produced by stressed corals. Finally, genetic modification of the coral microbiome or use of experimental or selective evolution to give corals an advantage in stressful environments. Alright, just to start with some of the basics of what coral bleaching is. Bleaching refers to the loss of color in symbiotic algae between the microscopic algae and corals. Normally, the coral and the algae live together in a mutually beneficial relationship. However, when the coral experiences stress, such as higher temperatures in the ocean, too much solar radiation, high pollution levels, or others, the coral gets stressed and expels the algae. Corals are not dead after this expulsion, however, they are much more susceptible to starvation and disease, and if they do not regain the algae and remain at high temperatures, they will eventually die. As you can see here on the right, this is kind of a graph depicting coral bleaching. It shows the healthy coral here, and then the stressed coral as it experiences a stressful environment, and then eventually the algae is gone and the coral remains bleached, or essentially white. So we are going to go through 4 bleaching mitigation strategies. The first one being marine protected areas, or areas where in our oceans where anthropogenic activity is greatly restricted or prohibited. The concept of shading or creating shade through clouds, mist, fog, or surface films to reduce solar radiation. The use of exogenous antioxidants to combat high production of reactive oxygen species. And then finally, assisted evolution and microbiome engineering, or experimental evolution. So to start with marine protected areas. So as we previously said, marine protected areas are areas completely protected from any human interactions. Marine protected areas shelter areas of undamaged reef and sources of larvae by providing areas with enough substrate for coral reef growth. So in any area of coral reefs, any ecosystems that involve reefs, there is a high variability in susceptibility, even within the same reef complexes. Understanding these patterns of susceptibility can determine environmental factors that vary susceptibility and therefore may enable coral reef biodiversity conservation. So essentially, studies have specifically chosen areas where corals show the greatest resilience, and they measure this to enhance natural recovery. So complete and ongoing protection of specifically chosen areas where corals show greater resilience to bleaching, along with measures to enhance natural recovery of neighboring areas where corals are most susceptible to bleaching and subsequent mortality, is the goal of future marine protected areas. So the graph here kind of demonstrates a lot of different benefits of marine protected areas. We are going to essentially focus on bleaching. So the non-marine protected areas are shown in pink, with the protected areas in green. This is a 20-year time series from Australia's Great Barrier Reef. And overall, they demonstrated that within marine protected areas, reef community composition was much more stable, the magnitude of disturbance impacts was lower, and subsequent recovery was faster as compared to those unprotected habitats, which are all very important things for coral reef conservation. So marine protected areas greatly increase the resilience of marine communities to natural and anthropogenic disturbances through trophic cascades and herbivory, essentially letting the reef grow and prosper on its own without any disturbances will eventually heal the reef. So we're going to be looking at shading, which is essentially creating shading through clouds, mist, fog, or surface films to reduce solar radiation during high-risk periods for coral bleaching. So as depicted in this figure, survival curves showing the did probabilities of coral bleaching over cumulative thermal stress measured in weeks regarding coral species and light levels. So those with 0% shade, essentially there was 0% not bleached. So all of them pretty much became bleached in the time where there was no shade, as opposed to those with 50% shade and those with 75% shade. So corals without shading experience a substantially higher rate of decrease in growth as well as bleaching than those compared with any degree of shading. All right, to further go into this, the shading depth relationship. Another study I looked at the relationship between depth and shading. So individuals at a much shallower depth were 2.5 times more likely to be relatively or severely bleached than those at much greater depths in unshaded microhabitats. And then corals in unshaded microhabitats at shallower depths were 1.3 times more likely to be moderately or severely bleached than those in shaded microhabitats. So this pretty much proves that in deeper habitats, especially in those shaded areas, are the most protected in terms of bleaching events. So this has important implications for the future, as we might see a shift of where coral reefs are kind of located. The strongest part of the reefs may be in the deeper parts of the ocean. And mass bleaching decreased significantly with increases in depth for overall coral community and individual reef coral species. Corals occupying shaded microhabitats, which were the dotted lines here on the right, also showed reduced bleaching. So our third mitigation strategy is the use of antioxidants to combat reactive oxygen species. So you might have kind of heard about this in the human diet, or if you've ever kind of heard someone saying that antioxidants are good for you to consume and they combat free radicals in your body, things such as blueberries, raspberries, all those things have a lot of antioxidants in them. It's a similar thing in corals. So free radicals or reactive oxygen species pretty much are toxic oxygen, and they may be a mechanism that underlays coral bleaching events. So they are unstable molecules produced by corals as a result of environmental or other pressures. And the creation of reactive oxygen species leads to the destruction of cells and the expulsion of the symbionts, essentially bleaching. And a couple studies I looked at, the conclusion was that a single dose of the antioxidant catechin greatly reduced free radical levels in the hosts and therefore reduced the loss of symbionts from thermally stressed corals. So exposure to antioxidants increased photosynthetic ability and the ability for the coral to retain the symbiont. And we'll look at a couple graphs here on the next slide here. So this graph here on the left shows the difference in photosynthetic ability, with those in group B or up top here not having any exposure to antioxidants, while those down here had a much higher photosynthetic capacity as they were exposed to antioxidants. And similarly here on the right, you can see the difference in coral treatment. The number of reactive oxygen cells is here on the left. It was much lower in catechin-treated corals, even under thermatic stress. So our final mitigation strategy we are going to be looking at is assisted evolution. Essentially, it's experimental evolution of coral-associated bacteria to confer thermal tolerance in coral hosts. As we know, bacteria are adaptable to various stressors. They have the ability to mutate very quickly as their short lifespan and high reproductive processes. So oxidative stress is a known coral bleaching related selection pressure, as we just discussed, and successfully enhancing antioxidant capacity in tested bacteria could confer this tolerance to coral hosts. Antioxidant capacity in coral targeted probiotics could increase and enable coral to have climate resilience. So essentially in this experiment, organisms were maintained under given selection pressure for several generations and adaptation is forced. And then this adaptation, which is a greater antioxidant capacity, is in the coral targeted probiotics, could increase and enable coral climate resilience. So it's kind of depicted here on the right, the most important steps being here in C and D, where the phenotyping and the changing of the bacteria as it's maintained for several hundreds of generations. It is then experimentally evolved. It is then experimentally evolved and it's re-inoculated into the coral microbiome. And the thermal stress is kind of transferred into the coral. So, kind of looking at a couple of risks and benefits associated with assisted evolution. There are several risks, as genetically superior corals may pose a threat to other marine life and cause unanticipated and unintended ecological issues. Essentially, if we start genetically modifying one organism, they may have too strong of an advantage over another and almost act as an invasive species, kind of create a negative cascading effect into other parts of the ecosystem. However, the benefit is that it can provide coral reefs with the vital capacity to adjust at a pace nearer to that of present climate change trajectories. And there are different levels of intervention. You can do selective breeding, where select stocks use an ambient environment and you kind of choose the best corals to reproduce. Or you can, as we previously discussed, modify the microbiome communities. Or you can even force evolution of the symbiote itself. There is a lot of different things you can do with this evolution. However, there might be posing a lot of different ethical dilemmas and kind of questions of genetically modifying our environment are raised and pretty controversial, as a lot of this technology is fairly new. All right, to just kind of talk about some policy briefly surrounding coral bleaching mitigation efforts. The EPA does apply its Clean Water Act to decrease land-based sources of pollution that degrade coastal waters and coral reefs that live in them. That kind of goes with the Clean Air Act as discussing greenhouse gas emissions and trying to reduce those will have a cascading effect onto our oceans. And the United States did form a coral reef task force to lead U.S. efforts to preserve and protect coral reef ecosystems. So, as we know, the major source of coral reef bleaching is warmer ocean waters globally due to increased greenhouse gas emissions. We know that our oceans are large sinks of our carbon dioxide in warmer water. It kind of all goes hand in hand. To reduce negative effects on coral reefs, we have to decrease greenhouse gas emissions. So under the Paris Climate Agreement, the United States vowed to cut emissions at least by 26% by 2025, which is nearing pretty quickly. And hopefully we will achieve those goals now that we are back in it as a country. And the broad goal of reducing emissions by 80% by 2050. And this can be done in several different ways. New, cleaner, advanced energy technologies, putting a higher carbon tax, higher carbon price could reduce fossil fuel use, retrofitting older buildings to be more efficient, and tackling sectors like air travel and shipping. So kind of curating those processes to use less fossil fuels to reduce our greenhouse gas footprint. And just quickly, these are my references. And to kind of just go into that, I like to look at what we can do individually to kind of protect our coral reefs, as we know they are very vital to our global ecosystem. So 10 ways that you can protect your coral reef: choosing sustainable seafood, making smart seafood choices, volunteering if you live on the coast, or even if you don't. We know that our watersheds are all connected to our oceans, so volunteering in your local watershed. Conserving water, that's probably the biggest one that you can do every day. Conserving water at any chance that you can will benefit our coral reefs. And through education, I think that's a really big one too, is educating ourselves on what is going on in the coral reefs, what we can do to save them, and how to make conscious decisions in our daily life. Thank you so much.